So this is the second video on tagging, and for this we need to use something called hidden Markov models. Hidden Markov models are these models where you observe some behavior, but what you really want to understand is what is the underlying cause of that observation, of those observations. And the idea here is that you observe a sequence of observations and you want to determine the sequence of states that led to those observations. So if we look at it in a diagram, we assume that any given state only depends on the previous state. That's an assumption we're going to make, and that we're going to call a transition probability. And we're going to assume that the observations depend on the actual state. We're going to call that an emissions probability. Now, a good example to think about this could be, for example, determining whether a dog is happy or angry, right? You observe wagging of the tail of the dog, and you have to check whether that's a happy dog or an angry dog, right? So, but all you have is these observations. But you know that if the dog is happy, it'll wag the tail. There's a probability that it will be wagging the tail. If the dog is angry, you know that there's a probability that it will be wagging the tail, and that probability might be a lot smaller, right? So by looking at the observations, say for example, wag the tail, did not wag the tail, did not wag the tail, wag the tail, the idea would be to determine whether it was happy, angry, angry, happy, or happy, happy, angry, happy, right? We want to determine that sequence. More formally, we said that the probability of this model, the whole probability, is the probability of seeing a bunch of states, a sequence of states, given with a sequence of observations. Now, the conditional probability of this, right, would be the probability of the initial state, x0. We have no observations for that one. But then, for each one of the other states, we're going to multiply the probability of that state, given the previous one, times the probability of the observation given that state. That's the emission. So it's transition times emission. Here we do the same, transition times emission for x2. And we continue all the way until the last state. Now, this looks a lot like our word problem when you want to tag something. You have a set of words and a sequence of corresponding tags for those words. So this is a verb, this is a noun, and so on and so forth, and you have a sequence. So imagine, like we were just talking, we have an input sentence, the observation, that's what you see, the words. And what you have to infer is what tag originated that word. Okay, what tag was I thinking when I used the word saw? Was I thinking on the instrument to cut trees, or was I thinking on a verb in past tense, the verb to see in the past tense, right? So we will use a hidden Markov model to define this probability of the words, O's, and the tags, Y's. I'm also going to call the words X at times here, and the tags are going to be Y. Now, what I want to find out is the most likely tag sequence for the words that I've observed, right? And I'm going to loop, one brute force approach would be to loop over all possible combinations of tag sequence and compute that probability based on the training data, okay? Now, if we think of trigram hidden Markov models, now my states, my transitions do not depend on the previous state, but on the previous two states, okay? So if I have any sentence from O1 to ON, any words, right? And a given tag sequence, right? Well, what I'm going to do is that, notice here that I have an n+1 here. The thing is that all the tags for the corresponding words, and the last tag is going to be the tag stop, just to mark the end of the sentence, okay? Then the joint probability of the sentence and tag sequence, right, will be using the formula that we saw here, right? If we just make it in the formula, and instead of having the transitions depend on the previous state, but we make them depend on the previous two states, we'll have something like this. We'll have the probability of a sequence of words together with a sequence of tags will be the transition probability is multiplied, so the probability of whatever tag I am on given the previous two tags, times the probability of the emissions, so the observed word given the following tag. Okay, we will do the following, because if we start at 1, we're going to have y1 given y0, and y negative 1, right, and y0. We're going to assume those to be a dummy symbol star, which is going to be what's the probability that a tag starts a sentence. That's basically what this will mean. So the parameters of the model, these probability estimations, are going to be a transition, okay, that's going to be any set of trigrams, any three words, right, including stop and including the star star on this side at some point. And the emissions, okay, they're going to be any word given a tag, right? So for any tag in the set of tags, we're going to call big S the set of tags, and V is going to be the set of words. So with those definitions, for example, we can compute the probability of a sentence. So for example, the sentence S is use a saw, okay? And I'm going to use this sequence to determine whether it's, what's the probability. I'm going to use V, dt, and N. And versus, I'm going to try another sequence. For use a saw, I'm going to try V, dt, and V. So this saw as a verb and this saw as a noun. And I will think, well, which one is more likely? Well, in order to compute the probability of this, I'm going to use, okay, what's the probability of, and then I look at all possible all trigrams with the tag sequence. So the probability of V given star star, because V starts the sentence, times the probability of dt given star V, so dt after you saw the start of a sentence and a V tag, times the probability of, or the parameter, right, estimation of a noun given that you started with a verb and a dt, times the probability that you see the end of a sentence stop after an n and dt. These are the transitions, and now I multiply all the emissions. What's the probability that use, here use, is tagged as a verb, times the probability that A is tagged as a determiner, A and its corresponding tag determiner, times the probability that saw is tagged as a noun. That will give me a number. And I can do the same thing with use a saw with the tags V, dt, V, right? The only thing that changes is these two probabilities here, because now stop comes after a V and a dt, as opposed to a noun and a dt, right? And this one is what's the probability of a verb following a verb and a dt, as opposed to what's the probability of a noun following a verb and a dt. And the other thing that changes is this probability of saw as a verb. Whichever is bigger, that's the most likely tag sequence for this. Now, sometimes, two things. So one thing would be to do a brute force combination of any three tags in the set of tags S for these words and compute these probabilities. Now, what we're going to find a lot of times is that these transition probabilities, just like the emissions probabilities, and now I'm using W to signal a word and T to signal a state because these are general things, right? So any transition probability, you might find that it's 0 because you never observed, say, for example, the trigram, right? Or you never observed a bigram there, right? So what we can do is linear interpolation smoothing, where we multiply the probability of the trigram here is you count how many times does the trigram of tags happen divided by how many times has the bigram of the last tag and the previous one happen. Okay, so how many times this one happens, right? So you can multiply that by some coefficient. Then you can have a different coefficient and you multiply the probability of the bigram. And then another coefficient and you multiply the probability of the unigram or the unitag, right? With having all three lambdas add up to 1, therefore we maintain the idea of a probability distribution here, where all these values add up to 1. This is called linear interpolation. So the probability of a word here, for example, if I don't find the probability of a noun following by a verb and a DT, I will multiply this by something. But if the trigram verb DT noun is 0, then I can still have some probability if I look at the bigram. What's the probability of a noun following a DT only? And that's going to have a multiplier. So that's going to be a smaller, that might be whatever probability, but with my multiplier, I'm going to make it smaller, right? Because it's less important. I wanted to find the trigram, not the bigram. But the bigram at least gives me an indication of whether it's possible to ever find the trigram anywhere. Anyways, the emission probability, you count basically how many times you see the word tagged as such, as whatever tag, divided by how many times you see the tag, okay? You can also smooth that one. For example, if I want to see what's the probability of P following N and V, I'm going to have lambda 1 times I count in my corpus, in my analysis, in my training data, I will count how many times I saw noun, V, and P divided by how many times I saw noun and verb. Plus, a second multiplier that's going to be a lot smaller, hopefully, that multiplies the probability of the bigram of verb and P, right? VP. Plus a lambda 3, which is an even smaller multiplier that counts how many tags, tag P's are there out of all the tagged corpus, right? That would be how I determine, for example, the probability of P following N and V. Now, if I want to find the emissions, right? So let's say I want to find the emissions of the word to as a pronoun, right? Well, or as a preposition, I will see how many times I see the word to tags as a preposition divided by how many times I see any preposition. So those are my estimators, right? We might find ways to deal with low frequency words. There are many ways to deal with low frequency words. One is you can see, you can first determine which ones are low frequency words. And let's say they're words that occur less than 5 times or less than 2 times, right? And you can use the low frequency words, you can map them. Either you can find a dictionary that tells you what the tag of the word is. You can look for prefixes. For example, if it starts with un or in, for example, unfathomable, invincible, they can be an adjective, right? If it ends in li, like surprisingly, right? It can be a superlative, it can be an adverb, right? Whatever. You can look at capitalization. So if it starts with a capital letter, then it might be a noun, right? You can look at hyphens. If it has hyphens, it might be an adjective. If it has digits, it might be a cardinal number, right? And you can improve the accuracy of tagging with these rules very much. Now, the Viterbi algorithm is a way to find this argmax without having to loop through all possible combinations of the tags that you want, right? That's the idea, because one way would be to absolutely go over all possible combinations of 3 tags and finding the probability, right? For all tags in S and and stop, right? And finding what the probabilities are. So that would be the brute force approach. So for all the tags in the corpus, and again, another set for all the tags in the corpus, because you need a triple loop, for example, right? For all possible combinations of 3 tags, and then you do all the, basically you do all the combinations. So let's look at perhaps a better way where we do not loop over all possible combinations, right? Let's have this intuition. So for example, we have this sentence here, Obama raises interest rates. And we put 2 stars at the beginning and stop at the end, okay? The idea will be for us to check the most likely next tag. So for example, we look at the probability of noun given star star, right? So this is the state, this is the Markov model, right? So these are the states. Probability of noun given star star times the probability that Obama is tagged as a noun. We compute that. That would be this path. We compute the following path. What's the probability of a verb given star star, and the probability that Obama was tagged as a verb. The next path is the probability that Obama is tagged as an adjective times the probability of adjective coming after star star, and so on, right? For all the tags that we have for this word. So let's say that we have probability of noun given star star is 0.2, probability of V given star star is 0.15, probability of J given star star is 0.15, and the probability of determiner given star star is 0.5, right? And let's say that the emission probabilities are Obama as a noun is 0.9, Obama as a verb is 0.08, Obama as an adjective is 0.019, and Obama as a determiner is 0.001, right? Let's say those are the probabilities, and we can compute which one is the most likely. And we find out that it's noun. Now, I'm going to go for all of these tags, and I'm going to look for, first, the probability that I see a noun followed by noun and star, and I see races tagged as a noun. Then here I'm going to look at the transition probability, so the probability of verb given noun and star, times the probability that races is tagged as a verb, and so on and so forth. And you can see in the example here, right, which tag will produce the maximum. And I'll find out. Let's say that one. Now I'm going to go and I'm going to do the same thing with verb, noun, verb, 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 and also and so on, right? So all possible combinations of these two. And I'm going to find the most likely path if it were a verb, and it's that one. I'm going to do the same thing for adjective. So I'm going to look at adjective and all of these. And I find that the most likely path is this one. And then I'm going to do the same thing with determiner and all of these. And you will see that the most likely path is that one, for example. Okay? Now what I'm going to do, and I'm tracking the most likely path, and it looks like there's a path here, right? That looks like that would be the most maximal path. And it kind of makes sense, right? Obama as a noun and races as a verb, it starts to make sense. Now I'm going to go into interest rates, and I'm going to look at all the nouns, the probability of a noun following a noun and an adjective, right? So now I'm just going to use the most likely. What's the probability of noun given noun and adjective? What's the probability of noun given verb and noun? What's the probability of noun given adjective and determiner? What's the probability of noun given determiner and verb, right? So I'm going to look at that, and I'm going to mark the most likely. So for noun, for verb, for J, and for D, right? Now I'm going to do the same thing for a verb. Verb with this, 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 and this, right? Verb here with this, this, and this, and noun. Then adjective with all of these, what's the most likely? And then determiner with all of these, what's the most likely? And I mark just the most likely. I keep track of the most likely. And then here, rates, I will look at, okay, each one of these tags with noun. Then each one of these tags with verb, each one of these tags with adjective, and each one of these tags with determiner. And I keep track of the one that gave me the maximum. And then I'm going to do the same thing with stop and all the previous tags, right? And I mark the one that gave me the maximum. And then the idea would be to trace back, okay? To trace back what would be the best probability distribution here, okay? So it might be that it goes to noun, from noun it goes to this determiner, from here it goes to verb, and here it goes to noun, and so on and so forth, right? What happens when you have competing arrows? Well, these arrows have different values, so you pick the maximum. That would be the idea of how to create like a little trellis. And the interesting advantage of this is that at any given time, you're only comparing, because it's a trigram, you're only comparing the probability of each state given the previous two. So you, at every state, you're only comparing a segment of the possible combinations, not everything. And you're only tracking the most likely. So for example, for this one, I'm comparing these, all of these with this and just that one, right? Just the maximum, not all possible combinations of 3, but all possible combinations of 2, and then the third one is fixed. So the Viterbi algorithm, the idea here is to define n to be the length of the sentence. N is going to be the length of the sentence. Then I'm going to define sk being all possible tags for the word k. Okay? S minus 1 and S0, the tags at position minus 1 and 0 are going to be a star. The tags for all the other words, let's say, are going to be just all the tags of the corpus. And we're going to define R, which is going to be a table that's going to have the sequence of tags so far, right? So this is an identifier for the table, right? The sequence of tags so far. And that's going to be basically the probability, the probability of the Markov model that I'm evaluating with the tags. We're also going to define this computation, this function. Now we're going to define a table of pi with the maximum probability of a tag sequence ending in tags uv at position k. Okay? The idea here is that pi of k uv is going to be the maximum, right? The maximum probability, the maximum of this function that we just looked at, right? Having the last two tags being u and v. Okay? With that in mind, the Viterbi algorithm, I'm going to present you the whole Viterbi algorithm. Let's say the input is a sentence, x1 to xn, and all of the parameters that you gleaned, transitions and emissions, from the training corpus. You're going to start setting the table at 0, star star at 1. That can be a dictionary or something that associates this with this number 1. Then you're going to define the sets. Basically, you're going to be star for set for the tag -1 and star for the tag 0. And then for all the other words, it's just all possible tags. Now, what you're going to do is you're going to go for k from 1 to n, for u, for each u in the set of tags, and for each v in the set of tags, right? So these two basically are for all combinations of two tags, right? And for each, basically for each word or each possible tag, for all combinations of two tags, evaluate this pi, given the position and the last two tags, as the maximum of the previous pi times the transition probability and emission probabilities of the previous current tag with the previous two, and you loop for all possible tags on the previous tag. Basically, you're doing the trellis. Now, this gives us a maximum, right? But what you really want to store is the actual tag that resulted in that maximum, the argmax, and you can store it in a separate table, for example, right? Then, at the very end, you set the last two tags as the argmax of pi with the last position and the last two tags, and the probability of stop following those last two tags for all possible pairs of tags. So once you have all this set, then it's just a matter of going backwards, okay, from length -2 of the sentence to 1, and you're going to do the tag for that word is going to be basically whatever the backtracking table tells you at that position with the two tags that came before that. And then you just return that tag sequence. For a trace of this program, please watch the next video. And a few notes, well, the running time, if I want to compute the parameters, right, is of the order of n times the tag set to the third, right? Because there's 3 for loops where we loop through all the tags. 1, 2, and then to compute this mag or armax, right, I'm looping through tags, right? I'm looping through tags here, right? So that's the third for loop for tags. And then there n times s square entries in the pi table to be filled in. So that's the memory, right? And to fill one entry is one loop over all the tags. So the total number of this is how we arrive at this runtime execution. I understand this. I think the debugging of the Viterbi algorithm is going to give you a lot more insights on how this is accomplished.